Today, let's talk about the universe. We're diving into the biggest, most mind-bending questions out there, the kind that stretch not just space, but your imagination. We're going on a journey to the very edge of what we know, to a place where the cosmos is expanding faster than we can explain, driven by forces we can't even see. It's going to get weird. Let's get into it. It's a question you've probably asked yourself. You look up at the night sky and wonder, if I just kept going, what's at the end? What's on the other side? It feels so simple, so obvious. But to really understand how the universe works, we have to unlearn our intuition, because the deepest answers don't come from solving the old questions. They come from realizing we've been asking the wrong ones. So let's start with the biggest misconception of all. We all pictured the Big Bang as a giant firework exploding in the middle of a dark, empty void. But that's not what happened. The Big Bang wasn't an explosion in space. It was the explosion of space itself. It happened everywhere, all at once. Imagine a balloon, not an inflated one, but a crumpled ball of rubber. You draw dots on it to represent galaxies. When you inflate it, the rubber expands. Every dot moves away from every other dot. But if you were a 2D creature living on that balloon, could you point to the center of the expansion? No. The center is inside the balloon, in a dimension you can't see. And the edge? There isn't one. Your world is finite, but it has no boundary. Now, scale that up. We are living inside a cosmic balloon. Asking what's beyond the universe is like asking what's north of the North Pole. Once you're at the pole, the concept of north just stops existing. If the universe contains all of space and time, there is no outside. The expansion is reality itself stretching. But here is where physics gets slippery. We are taught that nothing can travel faster than light. Einstein's special relativity is the ultimate speed limit. But that limit only applies to things moving through space. It does not apply to space itself. In general relativity, space can stretch as fast as it wants. This means there are galaxies out there right now that are receding from us faster than the speed of light. The space between us and them is being created so quickly that their light will never, ever reach us. They are forever disconnected from our timeline. Astronomers measured this speed using redshift. It's like the Doppler effect for light. When an ambulance drives away, the sound waves stretch out, lowering the pitch. When a galaxy moves away, the light waves stretch out, turning red. The redder the light, the faster it's going. We have found hundreds of galaxies with a redshift so high, they are effectively breaking the cosmic speed limit relative to us. But knowing that the universe is expanding is old news. The real mystery, the thing that keeps astrophysicists awake at night, is how it's expanding. For decades, we thought gravity would eventually win. We assumed that after the initial kick of the Big Bang, the mutual gravity of all the stars and galaxies would pull everything back together. We thought the expansion would slow down. But in 1998, two teams of astronomers looked at a specific kind of exploding star called Type 1a supernovae. These are standard candles. They always explode with the exact same brightness. By measuring how dim they were, we could calculate exactly how far away they were. They expected to see the expansion slowing down. Instead, they found the opposite. The supernovae were dimmer than they should have been. They were further away than the math predicted. The universe wasn't slowing down. It was hitting the gas pedal. Something was pushing back against gravity. something massive. This was the discovery of dark energy, and it changed the map of reality. Before this, we thought the universe was made of, well, matter, atoms, stars, gas. But we were wrong. We now know that normal matter, the stuff you, me, and the Earth are made of, makes up only 5% of the universe. Another 27% is dark matter, an invisible skeleton that holds galaxies together. We can't see it, but we can see gravity bending light around it. But the remaining 68%, that's dark energy, and it's a monster. Dark energy is pushing the universe apart. Dark matter is trying to pull it together. And right now, dark energy is winning. But when we try to measure exactly how fast that victory is happening, we run into a wall. A problem so bad, scientists call it the Hubble Tension. Here is the problem. We have two ways to measure the expansion rate of the universe. Method 1, the baby picture. We use the Planck satellite to look at the cosmic microwave background, the afterglow of the Big Bang itself. It's a map of the universe when it was only 380,000 years old. By looking at the physics of that early universe and running the clock forward, we predict the expansion rate should be 67.5 kilometers per second per megaparsec. Method 2, the latter. We look at the local universe, nearby stars and galaxies, and measure how fast they are moving away from us right now. When we do that, we get a different number, 73 kilometers per second per megaparsec. 67 versus 73. That might sound like a small gap, but in precision cosmology, it is a canyon. The error bars don't overlap. Both teams have checked their math 1,000 times. Both are likely right. And that is terrifying. Because if the early universe predicts one thing, and the modern universe shows another, it means something happened in the middle that we don't understand. Nobel laureate Adam Rees calls this a sign that the universe is misunderstood. It suggests our model of physics is broken. We are missing a piece of the puzzle, maybe a new particle, early dark energy, a flaw in gravity itself. And if our understanding of dark energy is wrong, then our prediction for the end of the world might also be wrong. For a long time, we thought the universe would end in a big freeze, everything just drifting apart until the stars burn out and the cosmos goes cold, a lonely, quiet death. But if dark energy gets stronger over time, a substance physicists call phantom energy, we face a much more violent fate, the Big Rip. In this scenario, the expansion accelerates uncontrollably. It creates a runaway feedback loop. First, it overcomes the gravity holding galaxy clusters together. The night sky goes dark as our neighbors drift away. Then it overcomes the gravity of our own galaxy. The Milky Way unravels. The sun is stripped away from the Earth. But it doesn't stop there. The expansion becomes stronger than the electromagnetic force. Molecules are torn apart. Atoms are stripped of their electrons. And finally, in the last fraction of a second, the fabric of space-time itself is ripped apart. Past, present, and future cease to exist. So, is that really our future? Is the universe destined to tear itself apart? The honest answer is, we don't know. The Hubble tension is a clue that there is new physics waiting to be discovered, a door we haven't opened yet. It tells us that the story of everything isn't finished. The universe is still expanding, but so is our knowledge. We get to live in that brief, beautiful moment where we are intelligent enough to ask the question, but not yet wise enough to know the answer. So stay curious, because the next chapter of this story might just rewrite everything.